Good afternoon, everyone. I'm Neil Boddy. I'm from Goldman Sachs. And I'd like to thank you very, very much for joining me this afternoon. There's a lot of good presentations going on today. In this session, I'm going to be discussing our shift from fairly traditional relational-based CRUD, create, read, update, and delete, in which the tables in the database hold only the most recent information that the system has, to instead managing our persistent state using a NoSQL system and a log. Now, when I say a log, I don't mean an application log or like a log4j-style log. What I mean is an append-only log in which the data changes are captured as events and then stored in that log. We found that with this log-based technique, we were not only able to access and utilize a much richer body of state than was the case when we were using incremental CRUD, but we were also able to lay solid engineering foundations that improved our ability to standardize, to create new opportunities for using the data, but actually also to build a more fault-tolerant and a recoverable system. Now, as someone who's been at the sharp end of many problems, where the data in the relational tables is not correct and we have to unwind that state, any solution that offers a greater ability to recover and more resilience to having it in the first place is going to be very, very appealing. Now, in many ways, building new architectures not using relational style incremental CRUD will be harder, because there's a whole bunch of new stuff that you have to learn. For example, there's going to be a new technology stack that you need to learn. Then there's also going to be new concepts that you need to understand. And then it takes a while to refine the techniques of using a new set of technologies. I, for one, tend not to do things right the first time. So again, this is one of the things we have to factor in, that it takes a while to use it and to do things in an optimized fashion. However, we did find that through the use of aggregate structures of data and using the NoSQL scalability features, that we are able to, and actually also more explicit modeling, that we are able then to kind of solve old and familiar problems in more scalable and sustainable ways than we had done in the past. So in this talk, it's going to be presented in the form of a case study, and I hope it will be of interest to anyone who is thinking about moving away from CRUD, and also to those who are just kind of interested in our experiences and our observations. Now, the context of the application, so that was really the introduction, the context of the application that we were developing was in the area of master data management. Now, I'm not going to dwell on that because it's not central to the topic of conversation. Indeed, the concepts and the techniques that we're going to be talking about is equally applicable to any application, but indeed a data-centric one. But this I just want to spend a minute on this really to kind of give the idea of what we were doing here. Now, in the area of master data, this is all about the processes, the tools, and the policies for mastering and creating the critical data of the organization. And it's really about kind of creating that single copy of the truth that is then used and distributed throughout the organization. And very broadly speaking, there's two kind of flavors of master data. So one is on the dynamic side, where the volumes tend to be quicker and there's significant changes regularly. So this is classically the area of products and customers, inventory management, accounts, companies. Now, in the area that I work in Goldman, the areas of sort of security, the master data for security products, such as equities and fixed income products, also various forms of contractual products, and also futures and options. So all these areas are different forms of investment instruments, and we'd expect the daily change to be quite significant and the overall volumes to be quite large as well. Now, on the other side, classically we have the sort of static reference data that doesn't change very much, like countries, currencies, options, and the enum types that we would expect in an application. Now, this is really the kind of typical processing arrangement that we would expect for this kind of master data application. So you may recognize it as the fairly standard Python filters or staged event-driven architecture, in which different stages or filters are interconnected with queues. Each stage is going to be a kind of a single responsibility component, possibly running on one thread or perhaps a few more if we need to improve concurrency. But each stage is really a kind of a fire and forget. And in this sort of arrangement, for master data management, we'd expect incoming data in the form of data from files or a database or even REST calls, and that will be the data acquisition stage. Then there might be pre-processing where we need to decrypt and unzip. Now, very often the data that we get is highly fragmented, and what we need to do is stitch it together again. So we would use staging. Then having done that, we need to transform the data into the canonical representation that would then be used throughout the rest of the firm. Following that, we need to do some lookup to update the existing data that's there. There will be some form of derivation and validation, and then sort of finally persistence. Now, the form that this architecture would then take is to then process either a specific batch, in which case it would only be complete when all the records have run end to end, so that'd be one job, or alternatively it could be implemented in the form of a continuous stream where there's data running through basically 24/7. Right, so the motivations for rethinking this. Well, until the last few years, the established technique for persisting data has been relational incremental CRUD. And this has certainly been the case in my world of master data. And indeed, we have hundreds of these flows, at least 600. They're by and large reasonably complex flows. So you might have a flow, the top one might be processing equity data, then the other one might be processing fixed income forms of data. Another one could be doing legal company information. And a characteristic of all of these flows is they're all about the data. They only exist for the data, and they're sort of producing the data that's then going to be used by the rest of the firm, and that data is critical. Another characteristic of the way that we tend to process is that data must be processed in strict sequential order, and I'll say a little bit about that in a minute. Now, some of the data that we process, like, for example, the fixed income products, can be very, very structurally complex. So a bond, for example, would have at least 300 attributes. And because of the many one-to-many relationships that you have on a bond, at runtime, you'd have many more than 300. You'd have an object graph with thousands of attributes. So although this arrangement has served us well, we have used it many times, why make things more complicated? Why introduce a different system for sort of persisting our state? Well, as you can see, we do have hundreds of these flows. All of them need to have different schemas because we have to store multi-structured data. And the thing about complex flows and variation is that variation hurts, and variation is expensive, and variation will find its way in when you need to have custom flows. So even if you use standardized libraries in that pipe and filters network, in the stage-driven architecture, even with those standardized libraries, variation will find its way in, and variation doesn't really scale well. Similarly, because of the variation, we need to have domain-specific experts to do things, and similarly, experts don't really scale well. Now, there's other large dataset operations that we have to do where we have to compare one large universe with another universe of data. And the dataset operations that are significant tend also to have a lot of variation in them, and that's something else that we wanted to try and solve. And as I alluded to a few moments ago, one of the challenges of this environment with CRUD-based data is where we have to process things in very, very strict sequential order. Now, in the introduction, I sort of alluded to the fact that a system that is tolerant to data faults and system failure, and also has the ability to recover quickly, is going to be very, very appealable. It's going to be very, very appealing. So when you break the state of a database and there's many tables in there, it's very, very difficult to correct that state. It's very hard to unwind. It's also very, very fiddly. It's unintuitive. It's error-prone. And it's costly. And when there's a high severity error hanging over you, it's also very, very stressful. So when we get data wrong in this sort of context, in a master data management area, the rest of the firm feel it straight away, and we have to then recover quickly. So we had a problem a little while ago where we were processing some equity data. So, for example, like ordinary shares from various different sort of companies. And there was either there was either a bug in that particular flow, or there was an upstream problem. But what had happened was, on a given date, like the 3rd of March, rather than processing the the equity data for that particular day on the 3rd of March, it picked up the data from last year and it then fed that through. So that would have then meant that thousands of records would have been in the correct state in the various tables in the database. Now, to recover from something like that then takes a lot of forensic analysis to understand, well, what data is actually incorrect and really what is the extent of the damage. Then you have to devise a plan for recovering that state, and doing that can also be quite sort of challenging, and you need to jump on various calls and liaise with the stakeholders who want to know what the ETA is of recovery. Then you've got to create a migration at the data level, which is fiddly and complex, and then execute the migration. Then when you do that, in a recovery scenario, you could be processing much higher volumes than you would normally process on a day-to-day scenario. So in those cases, you could find yourself exercising parts of the system that haven't been exercising that way for a while, and then you could end up running out of disk or memory or whatever it is that, various different sort of issues that then happen while you're processing. So in that particular case, whoever's recovering the state, the team of people doing that need to kind of handhold it, and it will be very, very slow. So processing, CRUD-based data like this in strict sequential order has certain limitations. And this is what I've tried to capture in this next slide. So what we have here is a typical kind of CRUD process. This is in the top right, where we have a stream of data coming in, D1 to DN, and the CRUD process is then, a lookup, because we often need to merge the incoming data with the existing data. Then the merge stage has to be performed, where if, for example, you have a complex structure, you have a parent and many children, the merge has got to figure out what are the new records need to be inserted, the ones that have got to be deleted and updated, and then finally the save. That's really the CRUD process. Now on the left, I've tried to illustrate what actually happens here when we do this. So I've got like batch 1, batch 2, and batch 3. Now these batches need to be processed in this strict sequential order. So batch 1 is adding an A, a B, a C, and a D. And here in the bottom, we then see what we expect the current state of the database to be, which is A, B, C, and D. We then make a change via batch 2. Now batch 2 is updating B, he's removing C, removing D, adding an E, and establishing an F. And then finally, our batch 3 makes a further update to D, to B, reinserts D, removes E, and now establishes a child element of F. So that's really what we want. Now, if for whatever reason we didn't process that data in the right state, in the right sequential order, we ran batch 1, then we ran batch 3 and batch 2, the effect of doing that would be, as we have in the diagram there in the bottom middle, where A is fine because A hasn't been updated. The version of B we've got is stale. D's missing. E is there, it's not expected, so it's a phantom record. D is a degenerate one because, sorry, F is a degenerate one because F should have had the child component G, but G probably wasn't inserted because of referential integrity. So in general, expected data is missing. We're going to end up with phantom data that we don't really want, some data stale, missing relationships, and unwanted relationships. And the thing about a database is that when this sort of thing happens, there isn't like a reverse patch, like a version control system, that we can then just apply and then recover the head of the database. But it's actually okay because, funnily enough, accountants have already solved this problem for us. And what makes it worse is that they solved this problem hundreds of years ago. When a mistake is made, then accountants don't go in and erase and delete the mistake. What they do is issue another transaction, a compensatory transaction, to correct the overall position, thereby retaining the full audit history. So developing systems though that need to be resilient to human mistakes is a broader subject, which I'm not going to sort of touch in detail. However, immutable append-only events in a log that by their nature of not actually changing do not do irreversible damage to the state are an important part of a solution seeking resilience to that kind of problem and recovery from those failures. So this next slide sort of illustrates the concepts of event sourcing and some of the things that we took inspiration from to develop the solution that we did. Now, event sourcing, very briefly, is an alternative and powerful technique for managing state. The DDD community, the domain-driven design community, will lay claim to having developed this, in which the state is constructed from the sequence of events that is then stored in the log, which is very different to CRUD, in which the tables and database hold only the most latest information that the system has. So I've got an example here of an individual buying a book and capturing that in a shopping cart for that in a classic table, CRUD-based table, and then the event log. So in this scenario here, our user is adding book 1, he adds a book 2, he adds a book 3, he adds another book 2, and then finally he then goes and deletes book 3. He doesn't want that. So in our shopping cart, we have what we expect. The cart is capturing, the latest information that the system has. It is the current state. Now, some observations about how we get to this current state are that as these events were coming in from the user, or these user activities, the writer thread for the shopping cart then had to understand and transform those activities. So when when a second book 2 was added, the writer thread had to understand, well, I need to interpret that and find the existing book 2 and recognize that event as an increase to the count of book 2. And similarly for book 3, he had to interpret that as book 3 is no longer wanted, find the book 3 record in the cart and remove it. So in this particular case, the writer is absorbing all of that complexity of the lookup, the interpretation, transformation, and then the save. But on the plus side, there isn't any work or there isn't any netting or complexity now for the reader. Indeed, the shopping cart in this form is very much optimized for the reader. However, we have lost information because in the shopping cart, we don't capture the intent. We're only capturing the outcome. We have lost the fact that the user was thinking of buying book 3 and then decided not to. And obviously at the database level, we would expect the database system to then apply the transactions to provide the consistency guarantees that we now expect from a relational system. Now, in the event log, it takes a very, very different approach. So we add a book, we capture the event, add book 1, book 2, book 3, add another book 2, and then finally remove book 3. So in this particular case, we're creating rich structures of data that we're now storing in the log, which is capturing a lot of information. Now, event sourcing tends to focus on capturing events at a level of abstraction that reflects the activities that are happening within the domain, within the application, and that's really what we're seeing here. So we're really kind of modeling those particular events as first-class citizens of the application, in which case it means that your software is more explicit and it's more closely aligned with the application that you're developing. And generally in software, things that are explicit is actually a good thing. Now, in the case of our writer, he's now just simply appending those individual aggregate events into the log. And now the reader is absorbing all the complexity of determining, well, what really is the state of the shopping cart. So there's more work now to be done for the reader. But information has not been lost. We have captured the full extent of what the user was thinking when they compiled that log. So that now opens up opportunities for a read model in which we could have multiple different queries and projections of that data. So we might do some analysis on it and then see, well, actually most users finally end up removing book 3 after they have added them. That could be because there's a problem with the site or book 3 is too highly priced. Similarly, it opens up the opportunity of secondary actions. So it might be that a week later, on that book 3, there's actually a discount. So we can now email the user who created this log and let them know and offer them the discount. But the important thing is that the secondary operation is entirely divorced and separated from the original activity of the user. Now, also from that log, because we have the full context of what happened, from a debugging perspective, it's easier to work with. And because we're not changing state, it's more robust. One other thing to mention about the log is that this kind of approach of capturing state, storing it once, reading it a bunch of times, and eventually throwing it away, offers more opportunity for scalability and performance. In this particular case here, we're storing aggregate structures of data which lend themselves to being partitioned and scaled across a larger cluster. And similarly, at the database level, there's less work being done to maintain the consistency across the relations in the database. Right, now state that is shipped around the enterprise and shipped between different companies is often chunked up into data sets or batches. And as we saw in the pipe and filters framework that we looked at before, that would normally consume one of these batches and run a job end to end. When the whole thing is processed, every record is processed to a satisfactory completion, then the overall job is complete. Now, at first glance, batch data doesn't offer much by way of inspiration. Effectively what we're doing here is parsing a file and dropping it into a database. But the thing about data is that the devil is in the detail. Data is quite hard to create good abstractions for. It's hard to model, and it's also very hard to standardize. But what we were trying to do with our problem of multiple complex flows is actually rethink the whole process from the ground up. And that was really an important part of our overall process in moving from CRUD to the log-based system. And we were looking to solve a lot of problems. So while a batch might just look like a collection of records, and indeed those records are very important in the sense that the records in that batch are the reason the batch is published in the first place, the reason that a data vendor is selling it to us, and the reason that we're writing all this software to consume it. But if we then drop the helicopter and look a bit more closely at the batch, we will then see that there's a whole bunch of interesting concepts and metadata within that batch which we can then exploit. So for example, a batch is not a batch. We have an illustration here along the bottom where one batch might represent a full snapshot of the information. So it could be all the equities that are currently being traded. It's the full universe of data. Then another kind of batch could be a delta, which is the next one. And a delta now has a dependency on the full universe, because the delta now has to build on the data that is in that full universe. The next one along could be a correction batch. Again, it is a batch. It will contain many records, but in this case, the correction batch now has a dependency on the delta because the data is issued relative to the delta because it needs to build on the delta. Another flavor, I'll stop in a minute, will be the partial delta. Now, in this case, our delta batch will contain all of the changed records, but it won't necessarily contain a rich copy of the data. It will only contain bits of the information that have changed. So the delta on its own doesn't have any meaningful information. It's only when we merge it in with the state that we have accumulated from the full snapshot can we do something with it. And to complete the sort of picture of the different flavors of variations of the batch we have to deal with, a vendor won't give us a batch of all equities that are currently being traded. What they have to do is partition the data according to some notion of an enterprise segment that could be at a market level or it might be at region level that I've illustrated here. So, for example, full Asia could be the full universe of equities for the Asia region, and then the next one, full Europe, will be the universe of data of those equities for Europe, but again, it needs to build on what we have in Asia, and similarly, full Americas needs to build on that, and then finally the delta file. Now, the thing that's interesting about this is that irrespective of the content of the batch, of the records in the batch, this batch is containing, the different forms of batches are containing a lot of very useful contextual information and metadata that if we started to exploit, and taking the sort of philosophy from the event sourcing approach, where we're trying to model things very, very explicitly to align our software more with the domain that we're then solving, we can start to solve old and familiar problems in more scalable ways. So we had been processing our pipe and filters architectures and our flows have been processing the batch data processing and understood how to process the records in that batch data for a good deal of time. But what that software wasn't doing is really understanding the concepts about those notions of batches. So that then meant that we would have to rely on tribal knowledge to know, well, what do we need to process? What order do we process in? Is it even safe to process a particular batch? And when do we need to do this? So we were quite keen then to start to, as part of employing the ideas of event sourcing, log-based state management, to try and seize the concepts of the batches within our software, so that we could then start solving these old problems we've been doing for a while in more sustainable ways. Now, to give you a flavour now of the kind of arrangement that we'd have to solve in practice in the top right here. So this is for a particular set of financial instruments where the data is highly fragmented. On the right-hand side, it's sort of fragmented 4 different times in 4 different sorts of files. Then for each sort of file, the data is further fragmented into North America and Latin, Europe and Asia. And then there's another form of batch, which is going to be the difference or the full ones that we were discussing. Now, finally here, what I have at the bottom is a sort of a formulation, a pretentious one, I admit, where what we're illustrating here is that really our problem is really about the accumulation of state, and that's really the superposition of all the records in these files up to a given point in time to understand what our state and what our universe looks like, rather than in the incremental CRUD where we just look at it and the system contains the current state. And thinking it in these terms, where our state is a full snapshot universe plus all the incremental deltas and correction files, thinking it in these terms starts to align quite nicely with the event sourcing approach with our shopping cart that we were looking at a few moments ago. So change events in a log form a natural time series, as we have seen in the case of that shopping cart. But now, to understand the log, you really need to understand the time in the log. Now, the business data is typically issued and published for a particular business date. That's really the effective date of that data, the date when as far as the business is concerned, they can start using that data. It takes effect. And that's illustrated here along the x-axis, in which we have business data that's available on Sunday, and it's published for Monday, Tuesday, Wednesday, and so forth. But that particular date doesn't really tell us, although we capture it in the log, it doesn't really tell us anything about when that information is processed. And that's another important aspect of the log. And the time when it's processed, we capture here on the y-axis as the system processing time. So just following this graph through, sometime on Sunday morning, early on Sunday morning, we process Sunday's data. That's point A. Now on Monday morning, the first thing we do is we reprocess Sunday's data. Perhaps there has been a reissuance of the data. Perhaps there was a problem with the processing on Sunday, and we need to redo it. We need to correct the state of the database. On Monday, we then, a bit later, rather than after we process B, we then process Monday's data, which is point C, similarly for D and E. But then on Thursday morning, the first thing we do is we reprocess Sunday's data, point F, and then on Thursday and Friday, we then process that data. So, if we wanted to understand what data was effective for Wednesday, we could then take a look at this log, and it's going to be this region here. It's actually going to be B, C, D, and F. And the reason it's F is because Wednesday's data was reprocessed on Thursday. But that is the latest information that we have for Wednesday. But if we wanted to know what data was effective for a business date of Wednesday, but as at Wednesday, and that's a slight variation of this log here, where it's going to be B, C, D, and E. Now, in our earlier shopping cart example, the problem that had to be solved was the immediate purchasing problem, and that's understanding the state of the shopping cart. So it was necessary for the reader, it was necessary then for the writer to then produce that information so that the reader could again go and perform the fulfilling operations that were required. Now, in our world of master data, we don't have that problem to solve, but the way that the data is often given to us in batch form is that it's very often highly fragmented, which is illustrated here. So we may have a batch of data for our car object, then we'd have a separate batch of data for the engine and the chassis and the cabin and the transmission system. So what we're modeling here is an aggregate that we need to stitch together the different fragmented data to construct that aggregate. Now, we wanted to do that because we made a choice, a design decision, that we would like to process at the aggregate level because it made more sense. And the aggregate has got lots of useful technical properties that I'm just going to allude to briefly. So the aggregate offers the unit of logical consistency. So if you wanted to validate your car, and you wanted to know that the engine that you've got is compatible with the chassis, you'd obviously need to have the car, the engine, and the chassis. And similarly, if you had a four-wheel transmission gearbox, you'd need to know that that transmission system is compatible with the chassis and the engine. So the aggregate provides a useful unit of logical consistency. It's also the useful unit of work for the processing in the pipeline and also for the downstream processing. It also lends itself to being the unit of atomic consistency stored at the database level, whether you store it in a NoSQL system or whether you store it using a relational one. You would expect to have consistency guarantees ensuring that the state is preserved correctly. And finally, it also offers an intuitive structure for the data to be looked at, to be analysed, and to be reasoned about. Now, if we had an event processing stream that I have here in the middle dealing with this information, at time T1 at the head of the queue, we would see, the main elements of the car coming through. Then at T2, we have an update to the engine and the cabin, I think it is. And then finally at T3, we have the final change to the engine. So if we wanted to look at the compositions of the aggregates at the different stages, T1, T2, and 3, we'd expect to see the information as we see there. So T1 is the initial representation of the data that's come through. T2 captures the update to the engine of the cabin, and T3 finally captures the last change to the engine in the cabin. So we used Mongo as our store for the log when we started modeling it like this. So for those of you who are not familiar, so Mongo is a document store, and the way it works is you create your structures of data and you store them as individual documents then in various different forms of collections. So we then use the collection as our log, which is illustrated here. So for that car example, where we streamed in the different components of the car at different points in time, in the bottom left we see what the header might look like. What the document might look like. We have a header information that might contain, technical information about the processing, and then we have the body information, which is the business data. And in this case, it's the one for the cabin. And then at a time later, when we have the final update to the engine, we have a document that sort of captures the aggregate information now for that individual engine, which is stored here in the body. So I just wanted to mention a few things about Mongo that we found worked reasonably well for us in this context. So first of all, because of our multiple different data flows and data structures that we had to deal with in different schemas, Mongo supports multi-structured data as documents. And it's schemaless. So although we had to have the notion of a schema in our application, obviously for the writer to write the information and for the reader to interpret the information, the code has got to be schema aware, but at the database level, we don't have to capture any knowledge about the schema. Mongo has some knowledge around indexes and secondary indexes and where the addresses of those are, but by and large, it's schemaless information. Low friction persistence in terms of storing those aggregate structures as documents. As I mentioned, we wanted to take inspiration from the idea of event sourcing and really start to model the domain more explicitly and capture them as events. So we captured the full information about the metadata of the batches. Is it full? Is it a delta? Is it partial? And so we then modeled that and stored those as aggregates in the database. Now, while that will be absolutely possible to do using a relational technique, I think it's notable that from a persistence perspective, it was relatively easy to construct the aggregate and then store that as a document in a consistent way. The ability to scale horizontally, so as I'm going to be speaking about in a moment, the log is significantly large, and Mongo makes it relatively easy then to kind of scale the data across a cluster, and you have multiple partitions. So from a volume perspective, we can add more and more partitions to give us the capacity. From a writer perspective, if we have a fairly data-intensive stream, if you've done your indexing and your sharding indexing correctly, then you would expect to have a distribution, an equal distribution of data across all the nodes in the cluster rather than having one particular node running hot. Then there's also the ability to scale the read load. So it isn't necessary for the read to go to the primary. If we're reading data, which is surely going to be sort of stored, and we're reading past data, for example, if you want to do a comparison with the universe at one point in time and another point in time, we can certainly execute a read on stored data on secondaries, so it just lightens the load now on the primaries. There's also sort of performance gains from executing on a cluster where an operation can be performed concurrently across the cluster because you've got more CPU power, resources, etc. A note about multi-node redundancy. Now, in a cluster, a high availability cluster, we'd expect to have additional redundant nodes really to support high availability. So if a node goes down, other nodes are available. And now for us, we wanted high availability, but also across regions. So across the US, the UK, and Asia. And one other thing to mention about the cluster is that it offered much lighter operations from a maintenance perspective. So because the data is sharded across a partition, every node has much less data on, simple things like backups and rehydrations and even applying indexes can then be much, much quicker in this kind of arrangement. And then from a development perspective, we found that the use of the Mongo aggregate, which is a declarative language for sort of defining a pipeline of operations that offers a MapReduce type capability, was actually very, very useful. Because although it's like MapReduce, it's very, very explicit, and we found that good for traversing the log and extracting the data that we then needed. Right, so deriving the state from the log. Well, it's all very well having a design principle that says what we want to do is separate the writer from the reader because it just makes it better for the writer, and then the reader's got a little bit more information, a little bit more work to do. And it's a good design principle, to do that potentially. But certainly from the reader perspective, he now has to do a lot more work. And the problem that we now had is that we had a very, very large log, with up to a sort of 1 billion sort of records in there, and we had to extract the data to answer various different use cases for our application. So what we did was embrace those ideas of event sourcing and create 2 logs. So we had one log that contained the business data, which is the log we see, the large log across the middle, the event business data log. And in that particular case, that would really only store the business data. The indexes would be very, very light, and the queries would be quite simple. So we didn't have to store a lot of indexing information to inflate the volume of data stored. But then we also created a log for the processing information. So to understand whether we're capturing, a full universe of data. What enterprise segment is it? Is it a delta? Is it a correction file? So this is the log that will then be much, much smaller because it's at batch, at dataset level. So for this, the queries might be quite complex, so we can drill in and pull out the different sets of data that we want. So it's going to capture the full sort of semantics of what we're doing. It's going to capture things like the start time and the end times. We'd expect to have rich indexes to answer all the queries that we want to execute on it. And as I mentioned, the data set is small. So the way that our pipeline then worked was to interrogate this, to find the data sets that we then want, and this is capturing all that rich semantic information, and then find pointers that will point to the data sets in the much larger log. And as we can see here, D0, so that would represent a run of data, a publication of data that we're not interested in using. So in this case here, if we wanted to know what our universe of data was, it would be F1, D1 and C1. So we would get the pointers and use that to find the data in the real log that we wanted. So this functional schematic gives a sense of the interpretation of that pattern and how it will be applied in a data flow to solve the different use cases for the storage of our data. So when a query would then be issued, we would interrogate that metadata log that's capturing all that semantic information in the metadata lookup here to find those pointers, the data sets that we want for locating the business data in the log. Now then, having established those pointers, we can then concurrently interrogate the information in the log. But as you can see, the log is not one whacking great log. It's actually a log which is partitioned across multiple different nodes, which means that every node is holding a lot less data, so you can have a much better ratio of RAM to disk and storage. And because it's operating concurrently, we can find the data sets and locate the items of data quickly. Now, because the data that we're capturing in an event log takes the form of a time series, one of the things that we need to do is to deduplicate a record. So we might expect, record 100 to appear many times in that time series. It could appear on Monday, on Wednesday, on Friday. And then we want to pick the latest one that is relevant for our query, and we can apply the 2D time that we looked at before to pull out the right record. Now, when our user in our shopping cart example decided that they didn't want book 3, they issued a tombstone to indicate that should be a delete in our log. Now, similarly in our case, to answer some of our use cases, what we would need to do, like if you wanted to know what the latest representation of identity 100 looked like, and 100 had been deleted, we would capture a tombstone for that, so we'd eliminate it from the data that we then put together. So we could then use this general sort of form of data flow to answer various questions like, what is the universe as at a particular point in time? What are the changes between a universe on this particular day and another day in order to find what are the inserts, updates and deletes? So this is a problem that we had solved many times using incremental CRUD. It's a large data set operation, and we had needed to implement it different ways to solve that problem, and it hadn't been done terribly elegantly. Similarly, we can interrogate the data and then narrow down our queries and find the data sets for particular enterprise segments. So universe of changes of equities for London market or Warsaw market only. In some cases, in recovery modes, we wanted to be able to replay, let's say, all the delta and correction files for the week. Similarly, we could then interrogate the state, find the data sets we wanted, and apply that data. But because we're using the deduplication approach and the elimination of tombstones, we would feed the records through that we had found and then be able to apply only the latest image that we wanted. So, for example, if ID 100 appeared on Monday and it appeared on Wednesday and Friday, and we want to rerun all our deltas for Monday to Friday, we only really want to take the image on Friday. We don't want to play through what's effectively stale data. And for identity lookups at a given point in time across history and reconciliations. So we were seeking to build a system that offered a more sustainable way of processing reasonably complex data that would take a long time to process, was quite data intensive. And overall then, these are our observations for using an event sourcing paradigm to do this. So we found that because we had a much richer body of state, we had all the history, we understood what data should look like at a particular point in time, in 2D time, we could perform the various operations we had done in the past in more sustainable ways. We had the full lineage of what had happened, we have good transparency and the opportunity for replay. Now, another use case that we've solved many times, or if you've got one universe of data coming in and another one, we want to calculate what actually are all the deletes. Again, a high volume set operation, have been done in various different ways. In this particular case, because we understood that when we process a full universe batch, and we're capturing the semantics of that in our metadata log, then we haven't got to calculate the deletes to clean up the database. We know that what we do in our log, we're resetting the sets of data, and any computation of state will be from that, the start of the new image of our universe from then onwards. That made a lot of difference. We've done that many times. It was complicated. In terms of stale data recovery, that worked very nicely. So if it's Friday and for whatever reason some data for earlier in the week was replayed in error, so if you replay Sunday's data, you would wind back the state of a CRUD system. In our particular case, then you'd have to recover it. In our particular case, if you did that and you ran through accurate data for Sunday, but on Friday, all you'll be doing is repositioning a different image of Sunday's data, but for Sunday. We could apply the 2D time and then pull out the data that we wanted. So there'll be zero impact, nothing to do. Rogue data. If we had the scenario like the equity flow that I was talking about before, where we ran through data from a long time ago, when there was an upstream problem, in this particular case, if we did that, there would be manual intervention required. We'd have to know that this had happened. But in this particular case, what we do is issue an event into the metadata to deactivate the batch that we weren't interested in processing, we wanted to ignore, and then all queries in future would then ignore that information. That was the delta in the metadata example. Yeah, so what we do is then that particular event there, the D0 event, we deactivate it. It will then be eliminated from all computations that we would then need to do. We had another challenge where we had high volume data sets that would take probably about 30 hours to initialize. And that was because we had dozens and dozens of files with a high volume of records in them, and we had to process them incrementally one by one and to make sure that went through sequentially. With this new system that understood the notions of the batches that we were then processing and the 2D time, we could run all of those in parallel. So then the overall time to run that information through was taking about 4.5 hours, the time of the longest batch to process. Now, the out-of-order processing is a slight variation of that. On Friday, you don't have to process Friday's data. You can process Sunday's data because it will find its way into the log. We understand the semantics of the log, so the reader can pick and choose the data sets that he wants. I mentioned the low friction persistence, that absolutely it would be feasible to do this in a relational system, but it was notable that it was quite easy to store aggregates in Mongo. Low friction concurrency. Well, we didn't, I mentioned this because we didn't really jump through any hoops to get reasonable throughput. In some quite high volume data intensive flows when we're using incremental CRUD, we had to make considerable investment in getting the throughput that we needed. In this particular case, we just needed to do reasonably sensible things at the right time, make sure that we had the right thread utilization, and our throughput was very encouraging. And indeed, the recovery time of sort of 30 hours to sort of 4.5, 5 hours also indicates that. And because we understand the full semantics of the data, and we understood that we've got full for Europe or Warsaw, London, or deltas, whatever they are, we could then enforce hygiene controls more easily. So if it was Friday and you wanted to reprocess Monday's data, it would be quite easy to detect that. And finally, the database maintenance operations, because the data was sharded, it was partitioned, it made it much easier to do backups and index builds, and general node recovery, and overall maintenance had a lot less friction. So there are our sort of observations from doing this, from using event sourcing and actually using Mongo to put as our main log. So thank you very much for listening today. I hope it's been interesting. Are there any questions from the floor?
Thanks. Two questions actually. One, did you consider any other database engines?
Yes, we looked at other forms of doing this, and also Kafka. But in our organisations, what we liked was that Mongo offered a good solution for high availability, particularly across regions and data centres. And in this particular case, because we're dealing with master data, we wanted to have a store that offered a good solution for kind of storing master data. And Mongo also offered quite a rich kind of query language. So for those different reasons, Mongo seemed to offer a good solution for this log-based technique. And when we looked at it further, it seemed to do what we wanted to.
Okay, thanks. Thanks. And the second question: do you retire all the events, or do you clean up, or do you?
Yes, we do.
Do.
So we have a retention policy, and the retention policy can be flow specific. But again, understanding the metadata, whether we have a full, the start of our universe, we can go through and remove data that's no longer needed. We were building a platform to serve many different clients. So different clients have different retention policies. Some have 2 years, some have a year, some will just have a few months.
Any other questions from the audience? Okay, so give it up for Mr. Neil Boddy.
Thank you very much.
Thank you very much.